This episode of CppCast is sponsored by BackTrace, the turnkey debugging platform that helps you spend less time debugging and more time building. Get to the root cause quickly with detailed information at your fingertips. Start your free trial at backtrace.io/CppCast. CppCast is also sponsored by CppCon, the annual week-long face-to-face gathering for the entire C++ community. Get your ticket today. Episode 110 of CppCast with guest Gor Nishanov, recorded July 19th, 2017. In this episode, we talk about some of the news out of the Toronto ISO C++ meeting. We talked to Gor Nishanov, Principal Engineer at Microsoft. Gor tells us about the C++ Coroutines proposal. Welcome to episode 110 of CppCast, the only podcast for C++ developers by C++ developers. I'm your host, Rob Irving, joined by my co-host, Jason Turner. Jason, how you doing today?
I'm doing pretty good, Rob. How are you doing?
Doing good. How'd your training go?
I think it went well. I got some great feedback, and maybe I'll, see which one I'm going to plan to do next in the future here.
Okay, sounds good. Well, at the top of every episode, I like to read a piece of feedback, and we got a lot of feedback last week. So, Jason, normally we get pretty good feedback on Twitter and Facebook and everything, and we did get at least one listener saying, he always listens to CppCast on his way to brunch, and he said, Qt. He said he enjoyed this week's topic about Qt without what makes Qt bad for C++ devs, and said it was enlightening as hell. But we got some other mixed feedback as well. I think we kind of stumbled on a little religious war with Qt devs. There were a couple who, I guess, were upset that we didn't press the CopperSpice developers on some of the changes they were making. And a couple different listeners pointed us to this article that does a comparison between Qt, CopperSpice, and this other library that you can use with Qt, which is called Verdigris.
Okay.
Yeah, so I'll put a link to that in the show notes, and if you are interested in reading about another library that works with Qt, it looks like this one changes the way it gets rid of mock, but it still creates the meta object generation at compile time. So it handles the mock problem a little bit differently than CopperSpice, is my understanding. So if you're interested in that, we'll put this link in the show notes, and maybe we'll talk more about that topic in the future.
Yeah.
Okay. Well, we'd love to hear your thoughts about the show as well. You can always reach out to us on Facebook, Twitter, or email us at feedback@cppcast.com, and don't forget to leave us a review on iTunes. Joining us today is Gor Nishanov. Gor is a principal software design engineer on the Microsoft C++ team. He works on design and standardization of C++ coroutines and on asynchronous programming models. Prior to joining C++ team, Gor is working on distributed systems in the Windows clustering team. Gor, welcome to the show.
Hey guys, great to be with you.
So, I guess, how did you end up on the compiler team?
Well, if I tracked down what I've been doing, I was always jumping between the languages things and doing some production at some point, getting frustrated with the tools that I'm using and going back. So I think initially in Russia, I was on a cross-compiler team that were doing software compilers partially for space industry. Then after Soviet Union fell apart, I started doing random software, like, for example, Ink Eat Forward WordPerfect. Back in the 90s, we had pen computers, and Microsoft had pen API. So you can take a WordPerfect document and then scribble on top of it with your pen, and then you can, send this augmented document. So then I went back to school, RPI, at Rensselaer Polytechnic Institute, where Alex Stepanov and Maser collaborated on the STL. It was all infused with C++. So in '96, I thought I learned how to use C++ properly. So I went back into the product team. So it was a Windows NT team. And after applying C++ extensively for 15 years, I got frustrated. So I decided to go back. And I mean, Stud Future is what triggered me. That like it's so wrong. I have to go and start working on that.
Oh, well, now I need to know if we should wait until the actual interview portion so you can tell us all the ways that Stud Future is wrong, or if you want to tell us now if you're just anxious.
Oh, no. No anxious. It's all, I'm now mild, I'm calm. But that what prompted me, at least, the asynchronous programming and tools that are not sufficient enough in C++ that I decided to go and try to help.
Well, I will bring up Stud Future in a little bit, but I've got to ask, while we're still talking about your bio, what was it like working in the space industry and compilers involved in that kind of thing?
Well, I was young. I didn't know. I simply was writing compiler front end, was modular, and also worked on a register allocator in our middle or close to the back end. But then there were people who actually communicated and were sending the data. I never interacted directly with the space industry.
Okay.
Oh, okay.
So what year was that you were working on that, if you don't mind?
Early 90s, maybe end of 89, 90, 91.
Okay. I was just thinking about automatic register allocation and how the register keyword has never really been terribly useful in my opinion. Was it useful back then in the late 80s, early 90s? Or were you still just doing what you wanted to do?
I was doing a modular front end.
Okay.
So modular. It did not have any register keyword. It's the register allocator that is doing lowering.
Okay.
After you're done with the syntactic sugar.
Right.
Okay, well, Gor, we got a couple news articles to talk about. We'd love to get your thoughts on these, and then we'll dig more into coroutines, okay?
Sure.
Okay. So this first one is Herb Sutter's trip report from the Toronto ISO C++ meeting that just finished up a couple days ago. And it sounds like this was a pretty eventful meeting. The big headline that came out of it is that the concepts TS has been merged into the draft C++ 20. Gor, did you make it to this one?
Oh yes. It was a very exciting meeting. So concept, for example, for a while there was a big struggle to get them in, but people were disagreeing about some of the natural syntax for them, and they wanted to have more to type, and eventually deciding to separate the natural syntax from the rest of the proposal.
And as of now,
it start moving forward, and Andrew Sutton and Richard Smith and Core was frantically carving out the proposal, because it's I think it's relatively unusual that such huge change was done on the working paper during the week. So they carved, then they healed the wounds, they re-reviewed the code, and it was approved for merging into C++ 20, or at least the working paper that targets C++ 20. Then, from the article and from the other reports is that we got 4 TSs out. We got three technical specifications, networking coroutines, and ranges. And finally, modules moved into the PDTS stage, which is preliminary draft technical specification. So a lot of stuff was moved during this meeting. It was fantastic.
So for our listeners who are familiar with concepts, if I understand correctly, in the proposal there was 3 different ways with which a concept could be introduced, and now we've removed some of them or something?
Yeah, we removed 2. So essentially, there is a full syntax, which looks like a template syntax, But additionally, you can say requires, and you put concept names in places where you had type name or a class, right, in the template introducer. But in additionally, there was a natural syntax or function-like syntax where you can simply write a function. And instead of saying int, you can say a number or something like that. And it will be essentially a template function with restricted template parameter to just the number concept. So that was removed. And then there is another version of introducers where you have some relationship between the concepts, which was slightly more complicated, but still less cumbersome than the full template syntax. It was also removed. So we right now have only one, the biggest one, and then people agreed that they really want the short syntax as well. It'll just take a little bit longer to get there.
Okay, so you think the short syntax will make it in after it stays in the TS a bit longer and maybe has some of the language changed a bit?
Oh, I really hope so. I think people initially want to have big in-your-face syntax, but after using it for a while, they get tired of it. They're like, okay, I know it's a concept. Okay, let me just write it simply. So I think that will happen.
Okay.
Just from the usage, people would start using with the heavyweight syntax, and they would want a lighter syntax at some point.
Was there anything else, maybe not related to coroutines, that you wanted to call out from Toronto that was big news?
Oh, yes. There were a few little things. Like one of them I liked was designated initializers. Have you seen those?
Yeah, I did see that.
Yes.
I was curious about the syntax. It has you do like the dot member name instead of just member name equals whatever value.
Well, it came from C, so there were three design goals for designated initializers, and one of them improved compatibility with C, because like if you look at Linux kernel, it's all over the place. So everybody using this dot field name notation. So because of that goal, we went with exactly the same syntax as C, but it is so much better than C.
Okay.
Really, let's see what you guys think. So in C, these designators, they're optional. So you can use on half of your members, you can say a name, .a, .x, and then others you just put numbers or whatever values are. In C++, it's you either use normal initialization or use designated initializers. You cannot do half and half. So if you choose to say in .x equal 5, you cannot just say 3 for y. If you go that way, you go all the way. Another cool difference from C is that in C you can do them in random order. That's one. And second, evaluation order of the expressions that you put there is unspecified. Well,
okay.
in C++, in C++, we're saying they must be in the order of declarations, and the order is left to right. I think it's wonderful.
Okay. So we're thinking about the fact that objects are going to be initialized in the order that they're declared inside the struct, regardless of how we did the initialization, designated initializers, right? But you're enforcing it by saying the designated initializers must be in the same order they're declared, correct?
Yep.
So, okay, then why don't we go and fix class initializer lists so that they are required to be in the order that they're declared also?
Well, one step at a time, but I think we put a foot in the door with this one. So essentially, designated initializers, I really love them in a way how they cleaned up the same facility which came from C. And there are other little tweaks like the one I described, which are very nice.
Okay. That's interesting. I'm going to have to play with that. Do you know if any compilers currently support that syntax?
Clang.
Clang does? Okay. I assumed it had been tested in some compilers already.
Well, the proposal came with Richard Smith and Chandler in the list of authors, so I assume that they actually implemented it before proposing.
Right, okay.
Okay, this next thing we have to talk about is another proposal coming out of Meeting C++, and this is for a C++ review community. And I thought this was a pretty interesting idea. Basically, if you want to, if you make a library and you want to get some feedback on it, there's a new subreddit set up, which is CPP_review, and you can make a post about your library there. And this isn't starting until August, so we'll have to see how it actually works, but you'll be able to, go on and look at this person's library, submit feedback, and hopefully the library authors get some good feedback. And at the end of the process, you'll maybe get a Meeting C++ review badge for your library to show that you were successfully reviewed.
Certification.
That was a neat idea.
Yeah. Yeah, I agree. It's a neat idea because the boost process is big and difficult. Not everyone wants to be a part of boost. So just having some way to say that, yes, this library meets some minimum set of standards or something, it's a good idea.
Yeah, and not every library should be a part of Boost. You might just have a very small library that just doesn't fit in there.
Or a very big library that you don't want to be try to go through the effort. Yeah.
Right. Yeah.
Well, I'm wondering how people will be able to donate time to do those things. For example, in open source community like Clang, you do it by barter, right? You review somebody else's patches, they review yours, or maybe you bribe them with gifts and other offerings or something like that. But since this certification process is not geared to any particular project, I am just curious how it will work out. I mean, it's a great idea. I want to see how it goes.
Sure.
Right.
Yeah. Hopefully, some people are interested in giving their time to it. Okay, and then we were talking about futures earlier. Sean Parent wrote this article titled "Future Ruminations," and he's kind of going into a deep dive about his thoughts about futures and the future of futures. And since we talked with you, Gor, about how you got involved in asynchronous programming, I was wondering if you had any thoughts on this.
Oh, it's a wonderful article, and there are a lot of good things there about cleaning up the interface to the future, treating it as a handle to work and consolation, which is very important. But I'm not sure whether futures will be something that we will be actually using in the future. So I do not see the future for the future. But I'm trying to avoid puns, but they just happen. With the future, it's very easy. But essentially, you can have several ways of writing your asynchronous code. One is using callbacks, right? And that is not very convenient, at least for some people. They hate writing state machines. Others probably would use coroutines, which are the same state machine, simply written in an imperative fashion. So, if you use coroutines, you don't need full functional futures. You just need some kind of ability to explain what happens after you resume the coroutine, and we can talk about it later. Mm-hmm. So, composition of your code using future with .then and other operations, I'm not sure there will be use cases for that.
Some pretty strong words.
Well, yes, because there is a much more powerful construct like a reactive string. I'm not sure whether you have seen RxCpp or reactive extensions in Java, JavaScript. But essentially, those are streams of values that appear in time. So imagine the timeline, right, going to the right. And then you have 0 or more values appearing at some point in time. And then in the end, your sequence either never terminates, so values keep coming, mm-hmm. or it terminates with an error, or it terminates because there is no more things. So for those reactive streams, there is algebra. There are hundreds of operations, and you have extremely expressive declarative programming model where you're describing what you want to do. And you can see, programs which is very difficult to write normally, takes 5-6 lines to write with those reactive strings. So I think that this will be the two extremes. For people who want to write declaratively, reactive streams will be something that people would compose in a similar way how ranges TS works, right? With ranges, you have those little combiners and you compose multiple actions that transform your streams or iterables, and in the end you get something else. But it's a high level description, so you don't deal with implementation details, you just say how you compose those operations. And similarly with reactive asynchronous streams, there are actions you can do, and there are a lot of them. So I think in the future we will see those two extremes. If you want simply to write async code and express your code procedurally as the procedural function, do that, if something else, do this or else, and then sometimes wait on a bunch of activities, and then do that. So that will be expressed like a normal function, but with co-await as the coroutine. And on the other end, we will have declarative programming with reactive stream. Future just not expressive enough. It is a workaround for the absence of coroutines. So I do not think that futures will be something that we will be using.
So the reactive streams, are they dependent on coroutines also, or is this a completely separate proposal?
It's a completely separate proposal, and they can interact with coroutines, but they're independent. So usually a coroutine would be on the consuming side. Is that, for example, in coroutines we have for await statement, which allows you to iterate on a asynchronous stream. So that was put there with the knowledge that reactive streams will come.
Okay.
So the coroutine could be on the consumption side of the reactive stream or on production side of the reactive stream. Or you can even have an element where you co-await on something and then yield. So we'll talk about that maybe in the coroutine part of the discussion. Okay. But you can mix await and yield in the same coroutine. And the result is a synchronous stream, because we can suspend and then yield values, but over in a synchronous fashion. We do not do it in a blocking synchronous fashion. So coroutines will interact with those asynchronous streams. But those two programming models, procedural and declaratives, they are both very useful, because they can express different things in a nice, concise fashion. And those are the two things that will, I think, remain. I am not sure what is the future for the future. Again, no pun intended. It's just that, how else would you say it?
Right.
Okay, so since we're talking about await and yield and everything, for listeners who haven't heard or aren't too familiar with the coroutines proposal, could you give us an overview?
Sure. So at the high level, coroutines are functions which get two more operations. So normal functions, they have two operations, call and return. That's all you can do. There is a call syntax, f, parens, and then you pass some parameters. And then inside of the function body, you have a return statement that you can provide a value to return back to whomever called you. So coroutines get two more. They have a point where a function execution can be suspended and control return back to its caller. And then there is a way to resume the coroutine, and how you resume it depends on the semantic of the coroutine. So in C++, unlike in other languages, we decided to make coroutines open-ended, is that the language does not define the semantic. I mean, eventually in the library we will get coroutine types that will have some defined semantic, but as it stands today, coroutines are just a language facility which allows you to annotate where in the function you can suspend, and give an ability, a glue, to add in library abstractions that will explain what happens when coroutine is suspended and resumed. For example, the simplest one would be a generator. It's a coroutine which produces potentially infinite lazy sequence. So from the outside, it looks like an iterable. So you say generator of int, f, and then whatever is inside. So you will use it the same way like you use any iterable that has begin and end. You can go to your range-based for, you can give it to any standard algorithm which takes begin and end. With ranges, it's even easier. You just pass this coroutine, which is an input range, to any algorithm which expects range. And then whenever your algorithm does plus plus on an iterator, it jumps back into the coroutine and continues from the point where it was stopped. So it is a way to write a state machine, but in a procedural fashion. So you write your code and say, co-yield some expression. When you reach co-yield expression, that value that is being yielded will become available to an iterator which consumes the result of the coroutine at star, at the reference iteration on the iterator. And when you do plus plus, you jump back into the coroutine right at the point after it was yielding something, and it'll continue. So this is... I'm sorry, I thought there was some question.
No, go ahead.
Okay, so, and this is similar to what we have in Python, I think now in JavaScript, in C#, in Dart, and in many other languages. So it's not unique in that respect. What is unique in C++ is how efficient they are, and that they are fully open. You decide what does it mean to yield. We don't have a prescribed generator. You can plug in your own if you dislike what we offer in the standard. And right now, just to give an ability to people to experiment and come up with the awesome generators that will standardize in the future, we don't even offer you a generator. But it takes only 15 lines to write. So, maybe 50 if you include the iterators and a lot of comments. So this is one use case. Another would be an asynchronous task. So it's what before you use callbacks, or maybe futures.then, is that you are saying, I'm going to call an async API, and when it continues, and when, for example, I'm trying to connect to a socket. Okay. And once the connection is established, you will resume the coroutine from that point. So it allows you to write code as if it was synchronous. And the only exception is that at those points where your synchronous code would block, you would use co-await to signify that you want at this point to suspend the coroutine. And then in co-await mechanics, there is a way to explain to the compiler how to resume the coroutine once the task is finished. So, and then so far we looked at two different cases, a simple asynchronous task and a generator. But you can mix and match, because it's you who define the semantic of those. So you can say, if your function contains both yields and await, then the abstraction it represents would be an asynchronous stream, which can produce values, but it can suspend in between producing the values.
Interesting.
I wanted to interrupt this discussion for just a moment to bring you a word from our sponsors. BackTrace is a debugging platform that improves software quality, reliability, and support by bringing deep introspection and automation throughout the software error lifecycle. Spend less time debugging and reduce your mean time to resolution by using the first and only platform to combine symbolic debugging, error aggregation, and state analysis. At the time of error, BackTrace jumps into action, capturing detailed dumps of application and environmental state. BackTrace then performs automated analysis on process memory and executable code to classify errors and highlight important signals such as heap corruption, malware, and much more. This data is aggregated and archived in a centralized object store, providing your team a single system to investigate errors across your environments. Join industry leaders like Fastly, Message Systems, and AppNexus that use BackTrace to modernize their debugging infrastructure. It's free to try, minutes to set up, fully featured with no commitment necessary. Check them out at backtrace.io/CppCast.
Now, I want to clear up something, if it's all right. You've mentioned ranges several times, and I think that you're saying like just a normal begin-end iterator pair like we're used to currently, but how does this interact with the ranges TS proposal? I mean, the ranges TS that's presumably coming up also.
It interacts wonderfully. Casey Carter written adapters, which allows to plug in coroutines into ranges, and it's even available on a wand box. So I can send you a link so you can see how coroutines plays with ranges. Because I think in classification that Casey did, coroutine is an input. Yeah, it's an input range, right? Because you can only read from it; you can never go back. And essentially, whichever algorithm can work over the input ranges, you can give to that algorithm the coroutine itself. And then the algorithms would pull the values out of the range, and every time you pull, you jump inside of the coroutine and continue from the latest yield point.
So that's we'll definitely have to share that link in the show notes if you can give us one.
Yeah, sure thing.
Something our listeners would want to see.
So, what's the current status with the coroutines proposal? Was there any big news for coroutines out of Toronto?
Well, it was published as a technical specification. We have now 2 implementations, one in Clang, another in MSVC. And Clang, we missed 4.1 by just, I think, a week. So it will be in whatever the release comes after 4.1. But, hey, if you can build your Clang from trunk, go ahead. And Eric Fizili here already added the library support, so we are complete there. You need to grab both the Clang and the library that comes with it. But if you don't want a library, that's fine too, because it's just one little file that is required for coroutines to work. So there is a little file that defines the glue which links language support with coroutine abstractions that you want to provide. And it's a very small file which links those two together. You can just cut and paste it. You don't have to even have an entire library.
So have you been involved in both Visual Studio and the Clang implementations of coroutines?
Yes.
Okay.
Yes. Especially in Clang and LLVM, because there, yes, I did probably most of the work. In MSVC, I had help.
Okay. Yeah, I thought I had heard that.
Well, hold on. Richard Smith provided initial implementation of the parsing of the coroutines, but then he got busy with something else. So I plugged in the backend. It's where the heart of the coroutine is. And added whatever was missing in the front end to work with the backend implementation. And the good part is that now LLVM itself has coroutines, which is in the backend. Thus, people in Rust and in Python and other languages which target LLVM IR can get the same benefit or as efficient coroutines within reason in their language as C++.
Yeah, that's what I was thought that I had heard, and you just confirmed that it's actually an LLVM IR thing. It's a primitive in LLVM, I guess, is to a coroutine.
Yes, so there is a bunch of intrinsics, and you can describe your coroutine in pure LLVM, and then LLVM will actually turn your function into a coroutine. And the reasoning behind is that we wanted coroutines to be very efficient. And initially I thought I can completely implement coroutines in Clang because it has this wonderful AST and you can party on it and rewrite, change it. But after some experimentation, we ended up roughly with the same decomposition into backend and front end as in MSVC, where coroutine is fully represented in LLVM IR as a function, and it travels through the optimization pipeline as a function. And the reason for that is optimizers are very good at optimizing functions. They are not very good at optimizing state machines. So essentially, we describe coroutine as a normal function. It is optimized like a normal function, but just before it is eligible for inlining into its callers, then we do the transformation of a coroutine into a state machine. So we delayed as far as we could the transformation so that we get most inline optimization opportunities as possible.
Can you speak to how efficiently MSVC is also able to do this?
I am not going to talk about that because, the reason is our initial implementation of coroutines in MSVC, the purpose was to verify the glue, to verify the model.
Right.
So we focused
MSVC
just to make it work.
So that was the prototype, and Clang got all of the benefit of knowing how the original implementation was done.
No, it's not a prototype. It's a production version. It's just that we optimized for different things.
Okay.
We were trying to prove the overall design, but it's still usable. It's just not as efficient as we would like to.
Right.
Yet. But in LLVM, we went into a different approach. We just said, okay, let's see, can we get it optimized the way we like? And that was the focus, because the rest of the coroutine design was already verified and vetted in MSVC. So we focused just purely on the optimization opportunities.
Okay, so we've brought up this optimization and all this several times now. So how much overhead is there in using coroutines, in this adding this abstraction?
Depending on the scenario, it could be zero.
Okay.
For example, in CppCon last year, I showed that generator optimizes into a constant. If you are iterating of a generator over a fixed range.
Right.
And even though in general case coroutines involve heap allocation, for common cases we eliminate those heap allocations. So, and the rule is very simple: as long as the lifetime of a coroutine is fully enclosed in the lifetime of its caller, we place the state of the coroutine onto the caller's frame. So thus, if you have a generator, 4x over some kind of fancy generator, then you loop over it. Then the entire coroutine is purely on the stack. If you use structured programming, and by that I mean that you break your big function into a smaller functions, even though you don't even call them more than once. Mm-hmm. It's the same thing. Now we're going with asynchronous task. So if your asynchronous task is broken into subtasks, which are broken into further subtasks, and you simply co-await on that subtask, again, lifetime of the subtask is fully enclosed in the lifetime of a task. So it becomes simply a state is a local variable on the caller side, and then all of the inlining works like normal. So for a whole bunch of scenarios, we are making them zero overhead.
Okay.
Since you have coroutines in MSVC now, do you know if anyone's internally using coroutines, and
yes.
Has it changed how they're programming? Are programmers at Microsoft really enjoying them?
Yes. We had several teams using them in production. We also have external developers using coroutines. For example, Tidal. There is music service Tidal.
Okay.
Some kind of music streaming something, and the unofficial Tidal streaming app is written with coroutines, and you can see on GitHub and search for CoreWait, and you will find them. And inside we have several teams using the coroutines, and also modern CPP. I think you talked with Kenny Kerr some time ago. It's all based on coroutines.
Oh.
Not only on the use side, but also on the production side. So to generate the projection, he uses generators.
Oh.
But on the consumption side, when people write async code, entire WinRT is asynchronous. So without CoreWait, it's extremely painful to work with it.
So it does sound fair to say that this is proven and you're using it. And so are you expecting that we'll see it merged into C++ 20 like Concepts was soon?
We have merge criteria, and one of the part of the merge criteria, one implementation not tainted by me. Okay. So one coroutine implementation which is done from the technical specification wording as opposed to, from talking to Gor, what does it mean? So, and to a degree, EDG might count as that Edison design group. But ideally, we would love GCC to implement it too, so we can compare and see who is faster.
That, I think, is an overlooked... we have the tendency to complain about not all the compilers being up to conformance in particular categories, whatever. But I think it's one of the key strengths of C++ personally that people complain about without realizing it's a strength, that having these competing implementations verifies that the spec makes sense and verifies that we, have solid compilers.
Right. So I think to streamline TS process, last meeting in Kona, there was a discussion of having a merge criteria. And once merge criteria are met, it's nearly automatic merge process. Not sure whether it will work in this way, but maybe. So in the case of a coroutine, criteria are one independent implementation, a bunch of tests so that people can verify implementation against the tests, and adapters so that whatever is already in the working paper interacts nicely with coroutines. So if we have future.then in the working paper of the standard, then we'll have adapters that will work with coroutines, and we will throw in a generator just in case.
Does the spec make any overhead guarantees? Or maybe to phrase a different way, is the test suite that you're working on going to have anything that tests the overhead of the implementation?
I think we will add one just for the kicks, because it is a bragging right. We cannot we cannot demand it to be that fast or that good, but it would be fun to compare compilers. Right.
It strikes me as one of the few core language features that, at least because I have a hard time wrapping my mind around what exactly it's doing, that is difficult to actually demonstrate why it's zero overhead. If that makes sense.
Well, just go to Godbolt and see what's going on. So.
Well, yes, always can do that.
Yes.
You've mentioned the coroutine specific keywords a couple times, like co-await and co-yield. Is the co_ going to be the final language? Because I know if we watch, one of your videos from 2 years ago at CppCon, you were just saying await and yield.
Yes, I fought valiantly, but I couldn't. Essentially, it started with yield. Yield was the problematic keyword.
Okay.
And some people felt that return is too confusing. So, and then for consistency, how about we'll add core everywhere? And now there is actually a benefit of having a core return, because unlike other languages like C#, Dart, and others that have similar await and yield keywords, they all require some kind of tag on a function. For example, in C# it's async. In Dart, it's sync star. In Rust, they're talking about fn star or something like that. So that allows them to give a different meaning to await or yield keyword within the coroutine, because they know the context. In C++, coroutine is just a function that has co-return, co-yield, or co-await. You don't have anything extra on a function signature or a function definition. And that is part of the design, because we wanted to have seamless interaction with the rest of the language. We did not want to have a different calling convention or change the type system. So from the outside, coroutine is a normal function. It is undistinguishable. from any other function. It's only the implementation. Oh yeah, yes. For example, assume that .then in some form will appear in the future.
Right.
And your function says std future of int f blah semicolon.
Uh-huh.
You have no idea whether it's implemented as a coroutine or as a normal traditional function. It's simply implementation detail. You can flip back and forth. So why did I go there? Oh, I know. I was going for explanation why Coroutine is actually useful. Mm-hmm. Sometimes you just want to write a do-nothing coroutine, essentially, that it never suspends. Maybe you just started typing it. So you can say Coroutine semicolon, and boom, your function is a coroutine. Or maybe Coroutine space 42. So thus you have a coroutine, and it doesn't require extra tag. So that particular usage of Coroutine made me less annoyed with co underscore.
Okay, so what is the difference between a function that always returns the same value and a coroutine that always returns the same value? I mean, like, if you just did co-return 42, like you were just saying.
Well, the function will be identical. Okay. Because coroutine is simply... No, that way around. Function is a special case of coroutine.
Okay.
So coroutine can do everything that a function can do, but better. It can do more things. But when it is doing exactly the same thing as a function, it is a function. Okay. And that is something that I'm trying to break consensus. No, so coroutines were absolutely awesome 60 years ago in 58 because they were understood as a better function, as more general form of a function. But then, after algol 60, stacks came around and block-scoped variable came around. And those were hard to implement without extensive compiler support. So people took an easy route. They implemented coroutines on top of user mode scheduled threads. And that is much heavier abstraction than a function. And at some point, people start calling user mode scheduled thread or fibers. They start calling them coroutines. Then they start disambiguating them with, it's a stackful coroutine. And whatever is not a thread, it is a stackless coroutine. But essentially, those are two different things with very different costs of usage costs. And right now, with compiler-supported coroutines, we're bringing those good coroutines of the old, which are generalization of functions back. And usage of coroutines as a cheaper thread is less.
Okay, so if you today, when you're writing code, do you just use coroutine, co-return? Do you take advantage of the fact that coroutines are a better function and just use them everywhere?
No, because there is a potential suspension involved. You probably have a different type that we use normally. So if it's a generator, you likely use some generator type and you want to yield. So it is likely that, if it's future, if you used to write a function that returns a future, you can switch to using coroutines trivially. But if your function never suspends, why do you want to return a future of int or some equivalent of future of int, as opposed to plain int?
Right. Okay.
You were talking about threads a moment ago. Is there any interesting interactions between coroutines and threads that we should know about?
Well, if you implement an asynchronous coroutine, the one with co-await, which is trying to represent some async activity, well, it's your choice, or the choice of the library writer, whether you will be resumed on the same thread as the one that got suspended or on a new thread. And you have to be careful there. And some people prefer to be resumed on the same thread, and that can be encoded in the await adapters which tells the compiler, what to do when await happens. But it might be surprising. TLS is one of the things which might switch when you go to a different thread, right? So if you read something from TLS, when you resume slightly later, you will be reading from a TLS for a different thread.
So for our listeners who are familiar, referring to Threadlocal storage.
Yes.
So you're saying if you have a Threadlocal object in your coroutine, you access that, somehow return it, whatever, and then the next time your coroutine is resumed, it's from a different thread. You're going to now have a different local state that you weren't expecting to see, effectively.
Yes, you will be consuming the Threadlocal storage from whatever thread is currently running.
Interesting.
Which is actually wonderful. Which is wonderful, because let me tell you what happens when it's the other way around. So, there are fibers, there is boost coroutine. So compilers in some architectures, thread local access is expensive. So they would go and cache an address of a TLS page in some of the registers which are preserved between function calls. And then imagine that you suspended that function in a stackful manner, which essentially means you have no idea that you got suspended, because some function 10 levels down did the suspend. Mm-hmm. And then you resume the coroutine on a different thread. So now that register points potentially into some other memory. So it is actually very dangerous not to do what happens in the C++ coroutines with regard to thread local storage.
Right.
So essentially with things like boost coroutine, if you resume your stackful coroutine on a different thread, it is undefined behavior if you touch
thread local. Like, you should not touch thread local at all.
Okay.
So I just want to make sure I understood one thing. If you're running a GUI application and you call a coroutine and you want to make sure you resume on the UI thread, is that something you can do?
Yes. Yes,
and what does that calling syntax look like?
It's all the same. It's await on something. And since it is the library that describes to the compiler what happens when you await, you can do things like you capture the current execution context, which threads you are running. And then when you resume the coroutine, you will simply say resume on that thread. But it depends on your environment. So coroutines were made to work with arbitrary runtimes. So as long as you can express that in your runtime, you can teach coroutines to interact gracefully with it. So coroutines come naked. It's just a compiler feature. But by design, it was meant to plug in to whatever asynchronous runtime you have, or UI runtime.
Okay. So do you think that coroutines are going to fundamentally change the way we interact with C++?
Only if you do async stuff.
Okay.
Maybe UI. And it will be easier to write iterables. Okay. So, like lazy sequences, it's another use case. But it's mostly, I think, those two. Asynchronous programming and lazy sequences. But otherwise, you'll be doing exactly the same way like before. Well, maybe one more. Coroutines also allow you to write clean code without exceptions, because every await point can be customized to work like if error go to end. So, for example, if you have expected of t type, which expressed either a value or an error, you can make so that when you co-await on expected of t, if it contains a value, the result of the co-await expression will be just t, whatever that value is. But if it is an error, it will propagate as the return value of the entire function, of the entire coroutine. So this is another use case.
Interesting.
Yeah, it was. I think we had 5 design goals: scalable, efficient, interact with C gracefully, open-ended, meaning customizable to whatever runtime, and the last one was exceptions are optional.
Interesting. There's definitely some people who will be interested in that.
Well, like driver writers. We did
Game
not want to make coroutines tied to the exceptions in any way. We can interact with exceptions just fine, but you don't have to. And because of that property, you can actually express something like exception-like nice clean control flow, because all of the error propagation will be handled under the covers by the library machinery that you explain to the compiler what happens when you call a wait unexpected of t, or maybe an optional of t, or whatever you want.
Okay.
Well, Gor, I think we may have gone over everything. Is there anything else you wanted to bring up before we let you go?
Well, one thing. Rob is actually doing the intro to the CppCast live, because I thought it's always the recording, because it was so identical every time, and now I'm seeing it live. It is incredible.
Huh.
Well, Gor, thank you so much for your time today. It's been great having you on.
Thank you, guys.
Thanks for joining us.
Thanks so much for listening in as we chat about C++. I'd love to hear what you think of the podcast. Please let me know if we're discussing the stuff you're interested in. Or if you have a suggestion for a topic, I'd love to hear about that too. You can email all your thoughts to feedback@cppcast.com. I'd also appreciate if you like CppCast on Facebook and follow CppCast on Twitter. You can also follow me at Rob W. Irving and Jason at LeftKiss on Twitter. And of course, you can find all that info and the show notes on the podcast website at CppCast.com. Theme music for this episode is provided by podcastthemes.com. Website at CppCast.com. Theme music for this episode is provided by podcastthemes.com.